Hello, I am Seema and welcome to part 18 of the chapter Organic Compounds, Some Basic Principles and Techniques. In this video, we are going to talk about the phenomenon of isomerism. And before I come to the definition of the phenomenon of isomerism, let us take one example and first understand it, and then the definition would make more sense to you. What is the formula for pentane? We know for any alkane there is a general formula, and the general formula is for alkanes is CnH2n plus 2. So whatever is the number of carbon atoms, if that is n, so in the case of pentane it is C5, H would be 2n plus 2. So 5 2s are 10 plus 2 is 12. So H is 12. So we express the compound pentane by a general formula that is C5H12. Right? Now it can be written in this way, that is CH3, CH2, 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 CH3. This is pentane. And when we did the nomenclature, we have seen the different ways in which it is written, and we have named it accordingly. But this would be simple normal pentane, right? In common nomenclature, we'd call it normal pentane. So pentane as a straight chain hydrocarbon. We could also write, now if we count this has got 5 carbons, and how many hydrogens? 3 plus 2 is 5, 3 plus 2 is 5, 10, and plus 2 is 12. So the formula is the same, C5H12, but you have now structurally represented it. If I write a compound like CH3, CH, CH2, CH3, and on the second carbon I put the branch that is CH3. Now this formula is also correct because every carbon is forming 4 bonds. Look here, carbon forming 3 bonds, and the 4th bond is with this carbon. This carbon is forming 3 bonds with other carbons and 1 hydrogen therefore, so it's forming 4 bonds. Similarly, this carbon is forming 2 bonds with 2 carbons and 2 bonds with 2 hydrogens. And this is a carbon forming 1 bond with another carbon and 3 hydrogens therefore. And similarly, this is a methyl group, 1 bond with 1 carbon and 3 hydrogens to complete the octet, that is the 4 bonds, the tetravalence. If we count the number of carbons and the number of hydrogen in this compound, what does it come out to be? 1, 2, 3, 4, 5, there are 5 carbons, and how many hydrogens? 3 plus 3 plus 3 is 9, 10, 11, and 1 hydrogen here, 12. So there are 5 hydrogens, 5 carbons and 12 hydrogens. Same general formula, but the structure is different. And now if I use the Iupac nomenclature and I name this compound according to longest chain rule, these are 4 carbons forming the longest chain, and this methyl group is forming a branch. So I will call it 2-methyl-butane. Right? This was pentane, this is 2-methyl-butane, but the general formula of both the compounds is the same. Come to the third variation. Let me now write CH3, CH3, and 2 branches of CH3 and CH3. This makes it neopentane. We know in common nomenclature we call it normal pentane, isopentane, neopentane. In Iupac nomenclature, how would I name neopentane? Neopentane would be named as, the longest chain would be this, and there are 2 branches, both methyl groups, so we'll call it on the second carbon. So we'll name it as 2,2-dimethyl propane. But again, let us count the atoms. There are 5 carbons, 1, 2, 3, 4, and 5th carbon, and 3, 3, 3, 3. 4 3s are 12, 12 hydrogens. Again, the formula is the same. But this is a different compound. Each one of these is a different compound. Although the general formula or the molecular formula for all of them is the same, but the structures are different, or the arrangement of atoms is different. And since the arrangement of atoms is different, their properties are different. I told you that the properties of hydrocarbons really depend mostly on their structure, and that is why their structure is so important. So this phenomenon that you have a molecule, or you have a substance which has a certain molecular formula, but due to the difference in the arrangement of the atoms in the molecules, you get different compounds having the same molecular formula. Such compounds which have the same molecular formula and only differ in their structure and therefore their properties are known as isomerisms. Just as we say, I and my sister are born to our parents. So me and my sisters, we are sisters. What is the relationship between us? That we are all born from our parents. So we are sisters. In the same way, they are all originating from one formula, but the difference in arrangement is making them kind of sister or siblings. And these siblings are called isomers. They have the same formula, the same DNA, let us say, only the arrangement is different and therefore their properties are different. And that is how it is with siblings. Each one of you is different. You look different, you act different, your nature is different, your behavior is different, you are in different professions. So the same formula but absolutely different compounds. And this phenomenon is known as isomerism. So how do you define isomerism? The existence of two or more compounds. Existence of two or more compounds having the same molecular formula but different properties. This phenomenon is known as isomerism. Isomerism can be classified into two categories. One is structural isomerism and the other is stereoisomerism. In structural isomerism, where we took this example, the arrangement of atoms, the bonding itself is different. The bonding is either in the form of a straight chain or in the form of a branch, or if there is a functional group, it is present at a certain position. It is basically the position or the bonding is different. The layout of the basic molecule, the arrangement of atoms is different. But in stereoisomers, the bonding is also the same, but their orientation in space is different. For example, today I just decide that I'm going to teach you, but I'm going to teach you in this side, from this direction. You can see the back of my head, you can see the back of my hand. I'm not teaching you with my face in front. I'm going to teach the entire chapter with my back towards you. So my orientation is different. I am still the same person, but I'm facing in another direction. So when the isomerism is due to the facing of atoms differently, that is their arrangement in 3 dimensions. When their orientation, the bonding is the same, yet their orientation is different. Such isomers are known as stereoisomers and the phenomenon is known as stereoisomerism. So let us now classify or understand isomerisms. The different types. The first is structural isomerism. Structural isomerism can further be classified into 4 categories. The first category is chain isomerism, which we just did. The second is position isomerism. The third is functional group isomerism. And the fourth is metamerism. So there are 4 types of structural isomerism. Position, chain, position, functional group, and metamerism. And there are 2 types of stereoisomerisms, that is geometrical isomerism and stereoisomerism or optical isomerism. It is there, I'll come to this later. Let us first understand the first category, that is chain isomerism. We took the example of pentane. In this, the arrangement of the basic skeleton itself is different. And since the skeleton, the basic arrangement of atoms is different, the chain is different. Either it is a straight chain or it's a branch chain. There's a single branch, there are 2 branches, there are more than 2 branches depending on how large the molecule is. If the arrangement or the different compounds are formed due to the difference in the arrangement of the skeleton or the carbon atoms, such isomerism is known as chain isomerism. So they are similar molecular, they have the similar molecular formula, but they have different skeletons. Just as in pentane we had a straight bone like the skeleton having a straight chain, in isopentane there was a branch in the chain, and in neopentane there were 2 branches. So the basic skeleton itself is different. So similar molecules but different skeletons would be chain isomerism. For example, you could take butane. Butane would be CH3, CH2, CH2, CH3. And you could take one CH3 and put it on the second carbon, so you'll get CH3, CH, CH3, CH3. So that would be butane, isobutane. So in this way, what you can get a number, you could take hexane, you could take other examples and start changing the chains and play it as a game and try to make as many isomers as you can. The next isomerism is position isomerism. As the name suggests, the name itself tells you the position. If you have a substituent or a functional group, okay, and I've told you what functional groups are in video number 8, I guess. I told you about functional group and I told you about homologous series. You remember in part 8. So when the functional group or the substituent, the position of the functional group, whether it is attached to the last carbon, second carbon, last but one carbon, or where in the chain is the functional group or the substituent attached. Now, the skeleton is still the same, but the functional group is attached to a different carbon. Such a isomerism would be known as the position isomerism, where the position of the functional group or the substituent makes the compound different. So the substituent or the functional group are present at different positions. For example, this is propanol, and in this the last carbon or the first carbon has, when you actually name it, this would be the first carbon, because the functional group, the carbon having the functional group, you would give it the lowest number. So this is propane or propane 1-ol. It has got alcoholic group on the first carbon. But here the OH is attached to the second carbon. So this is propane 2-ol. Now propane 1-ol and propane 2-ol are different compounds, although their formula is the same. And how are they different? Why are they isomers? They are position isomers because the only difference in them is the change or the position at which the functional group is present. Here in propane 1-ol, the functional group is present on the first carbon, and in propane 2-ol, it is present on the second carbon. You can practice lots of questions where you can see which kind of isomerism is it. The next is functional group isomerism. There are some functional groups which have similar formulae, which have the same, like one carbon, one oxygen, or an oxygen. So by the change of how the oxygen is bound or how that atom, just by the difference in the arrangement, the functional group itself may change. Such isomers, where due to the arrangement of the atom, which is not carbon and hydrogen, just because of the arrangement of atoms, they form two different functional groups, are known as functional group isomers. They are isomers and their functional groups are different, and the properties of functional group properties really depend on the functional group, and if they have different functional groups, they would be isomers, yet they would be very, very different in their properties based on the functional group. So functional group isomerism, they have different functional groups. The same atoms, due to the change in their arrangement, in the structure, they are forming different functional groups. For example, if you take the formula C3H8O, alright, C3H8O can be present as propanone, that is CH3CO CH3. If you write it in this way, it forms propanone. But if I write CH3, CH2 and CHO, if the CO is terminal, it becomes CHO, and CHO is an aldehyde, and RCOR, right, that is a ketone. So it forms either a ketone or an aldehyde, simply by shifting the CO either within the chain or terminally. If it is present on the terminal carbon, it forms an aldehyde. If the CO is present on any other carbon in the chain, then it forms a ketone. So this example, take a look. Propanone, if the CO is present on the second carbon, it's propanone. If the CO is present on the last carbon or the first carbon, it is an aldehyde. So propanone and propanone. The fourth category of structural isomerisms would be metamerism. In metamerism, different alkyl chains. Now, for example, you have propanone. On propanone, the functional group is here, C double bond O. And you have a methyl group here and a methyl group here. If you have longer chains, you may have the CO somewhere in between. But Isomers where the CO is present at different positions, that is like a functional group isomer, but the number of carbons on each side makes it different, are different. Such isomers are known as metamours. The different alkyl chains on both sides of the functional group, if the number of carbon chains on both the sides is different, such isomers would be known as metamours. For example, C4H10O. If you take this formula, you can write it as methoxypropane or ethoxypropane, where oxygen is in the chain. So if you have CH3, oxygen, C3H7, and here you have C2H5O, C2H5. So what is happening? After the first carbon itself, you have oxygen in the chain. And then CH2, CH2, CH3. Here you have CH3, CH2O, CH2, CH3. So in this compound, on both sides of the carbon, you have of oxygen, you have two carbons. But in this compound, in methoxypropane, you have a propyl group on one side and a methyl group on one side. So the difference is, in metamours, the difference is between the alkyl groups which are attached to both sides of the functional group. If the alkyl groups are different, although the formula is still the same, then such isomers are known as metamours. So these were the different kinds of structural isomers. Let us now come to stereoisomerism. In stereoisomerism, I told you that it is not the arrangement. The arrangement also is the same, but the orientation is different. The bond is coming out on this side. Instead of coming out on this side, if this particular bond decides to go on that side. So the orientation in space is different. And how does this affect? You will be studying about this in class 12. Yet, let me just tell you a little bit about it. They have the same constitution and sequence of covalent bonds. The bonds also are the same. They have the same formula. The bonds are same, but they differ in the relative position in space. The orientation in space is different, and therefore their properties are different. How would their properties be different? Let's take a look. The first kind is geometrical isomerism. In geometrical isomerism, we know that every carbon, if it is forming in this case it is sp2 hybridized. Why is it sp2 hybridized? Whenever you have a double bond in carbon, the hybridization is sp2. So what is the structure that will be around it? It will be a planar, triangular planar structure. So this carbon is forming a triangular planar structure here, a triangle here. Let me take another color. Yeah. It's forming a triangle. If you look, it's forming three bonds, and if you join the three, you get a triangle, right? Similarly, this carbon also is bound to this carbon, the methyl group, and hydrogen. So this is also forming a triangle. So you see, both of them, both the carbons are forming triangular planar structures. And now if we look at these two isomers, what do we notice? In this, both the methyl groups which are attached to both the sides of carbon, what is this compound? It is but2ene. The compound is but2ene. In this case, if you look, what's the difference between the two structures? In this, both the methyl groups are on the same side, right? This is hydrogen, this is methyl group, and this is the double bond, and on this side the methyl group is here. So both the methyl groups are here, and you have both the hydrogens in the bond going down in the triangle. So you can imagine these are two carbons, my two shoulders are two carbons. Both the methyl groups are here and both the hydrogens are here, forming a triangle. Both of them are forming a triangular structure. Now in the second compound, what do you see? A methyl group is here, and the methyl group of the second carbon is this shoulder, is going down. So it is transverse. It is not in the same direction. It is opposite to it. So this arrangement where both the methyl groups are on the same side is known as the Sis arrangement. It's a geometrical arrangement. So you see, in geometry, you find both the methyl groups are in the same direction, both the hydrogens are in the same direction. But in this, methyl groups are like this, hydrogens are like this, opposite to each other. Right? So this kind of an isomer, so the bonding is the same. Methyl group is attached to this carbon and a hydrogen is attached to the first carbon. To the second carbon also, methyl group and hydrogen are attached. The two carbons are attached by a double bond. It is the same. The skeleton is the same, but the only difference is in the orientation. The two methyl groups in the same direction would be cis isomer, and the two in the opposite directions would be a trans isomer. This kind of isomer, we call it cis-trans isomerism, or they are known as geometrical isomers. And then comes stereoisomerism. This is even more interesting, and you'll be studying this in details in your chapter haloalkanes and haloarenes in, no, not haloalkanes. Yeah, haloalkanes and haloarenes in class 12. You'll be doing stereoisomerism in far more details. You know, again, the bonding is the same, but the orientation is different. And the orientation is different, that the bond coming, one bond that is coming in front, the other isomer has the same bond going backwards. The structure is again the same. For example, if you take a tetrahedral arrangement like this, yeah, one bond, do you see this bond is coming towards you, and this bond, let us say these two are in plane, this is coming towards you and this is going away from you. If in another compound we had this bond rather coming forward and this going back, then that would be a stereoisomer or an optical isomer. Optical isomerisms are like mirror images of each other. If you stand in front of the mirror, you know, you raise your right arm and look at the image inside the mirror. You will see that you who is inside the mirror is raising her left arm. What is your right arm? For the mirror image, that is its left arm. The bonding is the same, the person is the same, everything is the same, yet something goes opposite. That's a mirror image. That is what happens in stereoisomerism. They are mirror images of each other. And such isomerism is known as stereoisomerism or optical isomerism. And they are known as enantiomers. What do they do? Why are they different, and why are their properties different? This is so interesting. Why are they different? And how do they affect the optical properties? How do they actually, in what way are they different when they are bound in the same way? Only the bond, they are mirror images of each other. How does that affect? You know, when light comes and the rays of light are in all directions, you know, when light is coming in to, let us say, a prism, light in all directions. When it passes through a prism, light becomes plane polarized, right? Plane polarized means that all the rays, they come in one plane. They come in one plane. It becomes polarized. This light is known as plane polarized light. When you pass plane polarized light through these isomers, that is the optical isomers, the two, that is one which is itself and the other which is mirror image. One of them is dextrorotatory and the other is levorotatory. Let me just come to that. When you pass it through one of the isomers, what happens? This plane polarized light, when you pass it through a solution of it, in a beaker, you're passing light which has been passed through the prism, and since it has been passed through the prism, all the rays are in one direction. It is known as plane polarized light. When I pass it through a beaker containing the solution, one of these isomers, optical isomers, stereoisomers, it twists the plane towards the right. If it twists the plane towards the right, it is known as the dextrorotatory isomer. And if I pass it through the other isomer, which is the mirror image, I will notice I will pass the same light through it. And that one, instead of pushing it, let us say that they pushed it 30 degrees to the right. This one is going to push, the second one is going to push the plane of polarized light towards the left by the same angle. If it was 30 degrees, this is also going to push it by 30 degrees but towards the left. That is the difference in their properties, that they affect light differently, and that is why we call them optical isomers. They affect the optical properties, they affect light, and how they respond to light, that is different in the case of optical isomerism. I would not like to go into details right here, but if you are interested in exploring more about it, go to the chapter in class 12, see optical isomerism or stereoisomerism that I have done in haloalkanes and haloarenes, and study more about it. So these were the different categories of the classification of isomers and the phenomenon what isomerism is. So with this, I'll wind up this video. If you found it helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.